Hello everyone. Here we present our paper for the runner-up place in the 2021 Evoked Emotion Challenge. This talk is divided into the following 4 parts: introduction, our approach at the challenge, experiments, and conclusion. Videos, as rich media content, are capable of evoking a range of emotions of viewers. With the booming of streaming platforms, creating attractive videos has become a key demand for both platforms and creators. In the 2021 Evoked Expression from Videos Challenge, we are required to generate 6 Hz predictions of 15 emotions from the given videos. This closely resembles the emotional impact of movies task in the medieval competition. Both requires the participants to predict the expected emotion of the general population with respect to a given video. This kind of dense labeling of the frames also reminds us of the task of action segmentation. Similarly, in action segmentation, we are required to distinguish the action type of each frame. The difference is that in action segmentation, we take the category with the maximum output. In EEV, we focus more on the different levels of each emotion and take the logits as the output of frames. When constructing the model for the EEV task, we could also use methods from action segmentation to perform the temporal modeling step. The best performing model in medieval task utilizes recurrent neural networks to model the temporal relation between frames. Temporal convolutional networks is also proved to be performant and more efficient compared to RNN in the action segmentation task. Like multistage TCN, it outperforms GRU and bidirectional LSTM on action segmentation task by a significant margin. In our submission, we follow the former approach and use bidirectional GRU to model the temporal relation between frames in our model. Here we explain our model in detail. We follow the model proposed by Zheng in the EEV dataset paper. We also extract the visual and audio features from the original videos. For visual features, we deploy the off-the-shelf swing transformer Swing L, which result in 1,536 dimensional features for each frame. For audio features, we use VGG-ish pre-trained on YouTube 100 million. The audio track of each video is first transcoded into 16 kHz mono audio and then using the method from AudioSet to compute the log-mel spectrogram. The 19.4 by 64 log-mel spectrogram is then fed into VGG-ish, resulting in an audio representation of 128 dimensions. The pre-computed features of each modality are fed into 2-layer bidirectional gated recurrent units without sharing weights. The bidirectional GRU builds the correlation in the temporal space. Comparing to unidirectional GRU, it takes both the past and future information into account, which enables us to form a better generalization at each time step for each modality. Each of our GRU module operates for 60 time steps. When we sample the input video at 1 Hz, this will give us a temporal perception range of 60 seconds. To fuse information extracted from different modalities, we adopt the late fusion strategy. The output of GRU is concatenated as the video representation. Context scaling is used to exploit the dependencies within the fused feature vector. In the end, another context scaling layer is added along with a sigmoid activation layer to calculate the final prediction. As for loss, we settled on a simple L1 loss. There will be more discussion on loss in the following slides. During the challenge, we conducted our experiments based on 2 key observations of the label data. First, the labels are noisy and contain sudden changes to 0. Second, The summation of the 15 emotions are not supposed to be 1. Each emotion is independent and range from 0 to 1. One successful experiment is linear interpolation. We train our model on 60-frame video clips with 1 Hz sample rate, which covers a 60 seconds time span. We consider 3 different strategies to obtain the dense prediction and 6 Hz for submission. First, we consider to keep the input frame numbers to 60 frames and change the sampling rate from 1 Hz to 6 Hz. The time span is also reduced from 60 seconds to 10 seconds, which compromises the inference results. Second, we keep the perception range at 60 seconds and sample the frames at 6 Hz, resulting in the input of 360 frames. In experiments, we find that the dense inputs harm the performance. Third, we can use the linear interpolation strategy to upsample the 1 Hz prediction to 6 Hz. Each emotion is upsampled separately. The results of 3 different strategies can be seen in the right table. It's clear that the last strategy with linear interpolation performs best on the validation set. For the final submission, we also adopt the third strategy and find that the sparse input sampling and the dense prediction interpolation are helpful. Here we report 1 failed attempt. From our observation of the expression labels, we find that it contains high-frequency noises and sudden changes to 0. These factors make the data hard to fit. Therefore, one straightforward idea is to use low-pass filters to filter out these high-frequency noises and ease out the sudden ramps. One example of Butterworth filter can be seen in the above image. Left and right image demonstrates 2 different filter configs separately. The left one removes more high-frequency components than the right one. This results in a more smooth filtered label, but also loses more information. To test this idea, we calculate Pearson's correlation coefficient between the filtered label and the original label in the second column of the table. In practice, we choose filter configurations that result in the highest correlation with the original data. When we train the model to fit the filtered label, this label correlation score can be considered as an upper bound of the model trained on the filtered data. While the smoothed labels are easier to fit, we observe that the model learned on filtered labels do not achieve better performance than the model learned on the original data. The last experiment is about different loss functions. In our model, we use a simple but yet effective L1 loss. One optional method is to use the KL divergence loss to minimize the distance between the predicted logit and the ground truth label. But as stated in the EEV dataset paper, each label is consisted of 15 independent emotion values ranging from 0 to 1. They do not sum up to 1 for each frame and certainly cannot be considered as a distribution. However, testing after the challenge reveals some interesting results as shown in the right table. The KL divergence loss outperforms L1 loss we use in our final submission on the validation set. We also tried another alternative correlation-based loss called concordance correlation coefficient, which can be seen in the left equation. Existing work has shown that concordance correlation coefficient performs better than error-based losses in terms of average concordance correlation score. Mu-x and mu-y are the means of the 2 variables, and sigma x squared and sigma y squared are the corresponding variances. Rho is Pearson's correlation coefficient between the 2 variables. This eliminates the square root part in Pearson's correlation and makes it easier to optimize. In our practice, although concordance correlation is more stable than L1 loss on the training set, it leads to a worse correlation score on the validation set. In this presentation, we present our approach for the viewer reaction prediction. Our model takes the advantages of both image and audio modalities to build the temporal correlation. During inference, we use a linear interpolation to generate dense predictions from sparse predictions. Albeit simple, the proposed method has achieved the second place in the EEV challenge leaderboard. In the experiment, we not only illustrate our detailed solution but provide our field study on different loss terms and label smoothing strategies. We hope it can pave the way for future works on reducing the noise in the labels or a new loss function to regularize the model training. In the future, we will continue to study more discriminative cross-modality losses, such as instance loss and clip loss. This is the end of our presentation. Thanks for your attention.